Good evening everyone. Today we are going to discuss about naphthalene. This is in the syllabus of the BSc 4th semester course of Dibrugarh University and the BSc course, the CHC05 paper, unit 9 of IGNOU. So basically what is naphthalene we are going to discuss in this class. Naphthalene, you may see the naphthalene balls as I have shown in the picture. We generally keep these naphthalene balls in our almirahs where clothes are kept for long times. This is because of this fragrant smell. The molecule is because the molecule is aromatic. So, besides this, naphthalene is a polynuclear hydrocarbon. That means more than one nucleus is there. The two benzene nucleus is here. So, before going into the details of naphthalene, you have to know what is polynuclear hydrocarbon. So, let us see what is polynuclear hydrocarbon first. So, polynuclear hydrocarbons are the hydrocarbons which contain more than one cycles together. If the both cycles are benzene, then this polynuclear hydrocarbon will be known as benzenate compound. And if one of them is benzene and but the other cyclic compound is not benzene, then but aromatic, then this type of polynuclear hydrocarbons will be known as non-benzenate compound. Now, among the benzenate compounds, we generally see that if the two benzene rings are isolated via some bonds or some skeletons, then it will be known as isolated benzenate hydrocarbons. And if both the benzene rings are fused together, not isolated via any link, then such type of benzenate polynuclear hydrocarbons will be fused rings. But we are restricted in our BSc level, we are restricted to study only the fused ones. That means these fused rings, that is fused polynuclear benzenate hydrocarbons. So they are generally naphthalene, anthracene, and phenanthrene. If the two rings are linearly attached or fused, then it will be known as linear. And if they are not linearly attached but via an angle, here you can see this is an angle here. So this type of fused ring system will be known as angular fused rings, polynuclear hydrocarbon. So this is the example of phenanthrene. But we are today in this class will be restricted with naphthalene. Okay. So let us see the structure of naphthalene. As we have already discussed the structure of benzene, we have shown in our earlier class while studying the structure of benzene that all the carbon atoms of benzene are sp2 hybridized. Here it is not an exceptional one. Here also the ring of naphthalene contains uh, 10 carbons and all the carbons are sp2 hybridized like that of your benzene. Okay. So now since all the carbons are sp2 hybridized, so every carbon atom has an unutilized p orbital containing one odd electron. So there is a pi cloud again here as that of benzene. Okay, this is a beautiful pi molecular orbital structure of benzene, naphthalene shown here. Now another interesting feature of the structure regarding the structure of naphthalene is that here two types of positions are here. This is the numbering should be noted. This is number 1 carbon known as alpha carbon. This is number 2, number 3, 4. Then leave the fuse carbons, and this number 5, 6, 7, 8. So 8 different carbon atoms, and these two are 19 carbons. Okay. So you can see here that the positions 1, 4, 5 and 8 are equivalent and are known as alpha positions. Similarly, the positions 2, 3, 6 and 7 are equivalent and they are also equivalent positions known as beta positions. So naphthalene has two equivalent positions, alpha and beta positions. While studying benzene, we have shown you that there is only one equivalent position. There is no distinguish between alpha and beta. In benzene, all the 6 carbons are equivalent, they are the same. But here in naphthalene containing 2 benzene rings, all carbon atoms are not same. There are two types of carbons here. We have already shown the 1, 4, 5, 8 are alpha and 2, 6, 7, 8, 2, 3, 6, 7 are beta. So remember the alpha and beta positions of naphthalene. Now, benzene is a molecule which is highly resonance stabilized. Similarly, naphthalene is also a molecule that is resonance stabilized. Here, since the two benzene rings are fused together in naphthalene, so we are expecting more resonance stabilization than benzene. Here we see there are 3 resonance structures of naphthalene where double bonds are exchanging their positions. If you try to draw the different positions of double bonds while trying to draw the resonance structure of naphthalene, you will find that you are able to draw three particular structures known as resonance structures of naphthalene. Now, the resonance stabilization energy of naphthalene is found to be 63 kilocalorie per mole. Now, let us see one interesting feature of naphthalene here. This is the carbon 1 number position, this is carbon 2 number position. The C1 C2 bond is here double bond. Here in this structure it is also a double bond, but in this structure it is found to be single bond. That's why it is found that the C1 C2 bond has more double bond character than that of C2 C3 bond. Hence the C1 C2 bond order of naphthalene is greater. It is found to be 1.36 Armstrong, which is found shorter because it has more double bond character than this has more single bond character and is found to be 1.40 Armstrong. This question is often asked in your exams, that why the two bond lengths C1 C2 and C3 C4 are not C1 C2 and C2 C3 are not equivalent in length. Why? This is because of this type of resonance structure or double bond character. Okay. Now let us quickly move to the preparation of naphthalene. The first method for preparation of naphthalene is by the Howard synthesis. Howard is a scientist who discovered uh, naphthalene by using two organic reactions. They are known as phenol carbacylation reaction and Clemmensen reduction. Now let us see how Howard synthesized naphthalene. First, Howard utilized the phenol carbacylation reaction, here benzene and here phthalic anhydride. Phthalic anhydride is the acylating agent in presence of aluminum chloride phenol carb reagent. So acylation is done via this bond COOOH. So it will be attached to any one carbon of the benzene. Let us suppose that this carbon acylated is acylated. So here CO, CH2, CH2, COH is the acylation is done. Next, say this is a ketonic group. We can reduce this ketonic group via Clemmensen reduction. We know Clemmensen reduction, amalgamated zinc in presence of HCl. If you do this Clemmensen reduction, then this CO group will be converted into CH2. So we have done here from this step. In this step, we have done Clemmensen reduction. Done. In the next step, we are giving a condensing agent like sulfuric, concentrated sulfuric acid, hydrofluoric acid. So that here we have a carboxylic acid group COOH, that is one OH group is here, and at this particular adjacent position one hydrogen is there. Okay, if you fuse in presence of acid dehydrating catalyst, then what will happen? The hydrogen of this position and OH of this position will be removed as water molecule, and this carbon will be attached to this. That means this molecule becomes cyclized. So this becomes cyclized and this is known as alpha tetralone. Now this alpha tetralone is again a ketonic compound. You can do another Clemmensen reduction so that this carbonyl gets converted into the CH2 group. Okay. Now this particular compound where there is no double bond in the second ring is known as tetralene. Now if we can do aromatization of this particular compound tetralene by using palladium in presence of carbon dioxide and heat, we are getting this ring aromatized. So this is the overall Howard synthesis by which we can easily synthesize naphthalene. Let us move to another method. Here you can see the second method is from 4-phenyl but-3 enoic acid. This is the structure of 4-phenyl but-3 enoic acid. If we do directly concentrated sulfuric acid condensation, as I have shown in the Howard synthesis, this OH and the hydrogen present in this position will be removed as water molecule, and this will be cyclized like this. Now this cyclic ketone, we can do enolization of this. If we do the enolization of this ketonic group, a double bond will be attached to here and this will becomes OH. So this will go to alpha naphthalene. As we know, phenol, if we do zinc distillation of phenol, we are getting benzene. Similarly, if we do zinc distillation of alpha naphthalene, this OH containing benzene ring will be converted into the benzene ring, and ultimately we will be getting naphthalene. Okay. Now in exams, often it has been often asked that how to synthesize 1-alkyl naphthalene by Howard from benzene. Okay. Now by Howard synthesis, we can synthesize naphthalene from benzene. We have already shown. We are repeating here. First up, do acylation. You do acylation, you will get this. Do Clemmensen reduction, you will get this. Then do condensation in presence of concentrated sulfuric acid, cyclization to give alpha tetalone. We have already shown in the earlier slide. From this step, that is from the formation of alpha tetalone, the reaction is somewhat different. So what we do here, you do, this is a ketonic group, so we do general Grignard reagent reaction. So here it will be OH and this will be R. So R and OH group will be introduced. This is general carbonyl reaction between carbonyl compounds and Grignard reagent. I hope you easily understand this. Now, if we do distillation in presence of selenium, then this ring becomes aromatized and OH group is getting eliminated as water molecule. Okay, now aromatic ring is obtained and R is attached one of the carbons. So we are getting one alkyl naphthalene. Okay. Now moving into the chemical properties of anthracene. Now, it should be naphthalene, not anthracene. Sorry. In naphthalene, electrophilic aromatic substitution reactions occur preferably at alpha position. Now, why it is? So now let us see. We already know that anthracene has two positions, alpha positions and beta position. Let us see the attack of electrophile at C1 first and then C2. When we see the attack of electrophile at the C1 position, that we will see the positive charge gets placed here. It is resonance stabilized by overall 4 resonance structures. But while we do the same thing in the by attacking the electrophile at carbon 2, we'll be getting only 2 resonance stabilized carbo intermediate carbon. So attack of the electrophile at alpha position is much more stabilized by resonance. Hence, in an naphthalene, electrophilic aromatic substitution preferably occurs at C1 position. So this is the reason, the resonance stability of the carbocation intermediate. Okay. Now we have seen that electrophilic aromatic substitution reactions occur at C1 position. So if we do the general electrophilic aromatic substitution reactions, we will be expecting the reactions to occur at 1 position. So first of all, if we do nitration, nitro group is introduced at the 1 position, correct? If we do bromination, then it will be introduced at the 1 position. A very little possibility of 2 position also, but mainly 99% 1 position. If we do acylation, but here one thing is here, if we do acylation in presence of carbon disulfide, it is getting at 1 position, and if you could do the same reaction in nitrobenzene medium, you will be getting it at 2 position. We will show in the next slide why it is so. If we do sulfonation, sulfonic acid group is attached to the carbon 1 position. If we do the same sulfonation at 160 higher temperature, then it will be, you will be getting it at 2 position. Okay. So what is the solvent effect? So this is a big molecule nitrobenzene. So after formation of the complex with CH3COCl, the reagent cannot approach towards the C1 position because in steric interaction. So it automatically attacks at this position. So while using nitrobenzene medium, the reaction occurs at 2 position. Next, another fact we have shown in the earlier slide, that the sulfonation at low temperature you will give you one substituted product, and at high temperature will give you two substituted product. Now the main product, why two substituted product is formed at high temperature? Because it is a thermodynamically controlled product. Why it is a thermodynamically controlled product? You will see at one position this sulfonic acid group is getting interaction from these two hydrogens, steric interaction, so it is not feeling not comfortable. But this is sterically stable. That's why at high temperature this thermodynamically stable control product is formed. But at low temperature this kinetically controlled product is formed. Okay. Another reaction, Bukhara reaction. If we do reaction of alpha naphthol with ammonia in presence of ammonium sulfide, we will get 1 amino naphthalene. This is a very good, very important reaction while being conversion from phenols to amines. Then chloromethylation is another electrophilic aromatic substitution. So chloromethyl group is introduced while using formaldehyde in HCl. Okay. This is oxidation. The last reaction I have shown here about naphthalene. If we use different oxidizing agents, you will be getting different products. You will have to remember this. If you use alkaline KMNO4, you will be getting thalonic acid. If you use acidic KMNO4, then you will be getting phthalic acid. If you use chromic acid, then you use 1,4-naphthaquinone will be formed. If you use oxygen inhibition vanadium pentoxide, then you will be getting this product. So different products are formed at using different oxidizing agents. The last reaction we are going to show here is the ozonolysis, where while you will be doing ozonolysis in presence of zinc, then you will be getting ThLLDL. So this is all about the naphthalene, the synthesis and properties. Thank you very much for your kind attention. Thank you.